The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Hope everybody's doing well today. Thanks for joining us for another webinar on our AMS, continuing AMS series of webinars. Today's webinar's title is Advanced 4-Axis Machining. My name is Joe Anand, and I'm the product manager here at MecSoft, for those of you who don't know me. As usual, I'll be joined by Uday Honalagare, our support manager, who's actually going to be doing the demo today. Before we get started, a few items I would like to point out. The recording of this webinar will be made available to all the registrants in a couple of days. We'll clean it up, post it on YouTube, and send you a recording link. And then as the webinar is underway, you can use your questions window, which is pointed to it by that big red arrow, to enter your questions. I will be in the background monitoring these questions window, and I will be answering them as to the best of my abilities. And also, if we need to stop with you during the demo, and if there's sufficient time, we can do that as well. And then if we do have time, we can also reserve the last 10 minutes for any specific questions that you might have. So as I mentioned, today's topic is Advanced 4-Axis Machining. The last webinar was the introduction to 4-axis machining. And if you haven't watched that, I would highly recommend watching it in tandem. Actually, you should watch that before you watch this recording, or might have been a good idea to see it before joining the webinar. In any case, the topics will be covered today are 3+1 machining, which is basically index 4-axis machining, somebody might call that, followed by parallel roughing and finishing, and then projection pocketing, which is also either mostly used for finishing, but can also be used for roughing as well. And then rotary instancing, which is a pretty nice feature, taking 2- and 3-axis operations and actually indexing or instancing them to run on a 4-axis machine. And then some of the advanced topics are the drive surface machining, and then R-level finishing, which is similar to the horizontal finishing in the analog in the 3-axis world. And then finally, some advanced options like feed rate options for 4-axis. I think there was a question that came up in our last webinar, and so we decided we'll address that here. And then 4-axis options as well, some of the UI options and machine control options that we have in the system. So without any further ado, Uday, it's all yours.
Thank you, Joe. Hello, everyone, and thank you again for joining us today for this month's AMS webinar series. We will be covering the advanced 4-axis machining topics in today's webinar. First, I will be starting out with the index 4-axis machining, or also known as 3+1 machining. And we'll cover this in one of our CAM products. We'll be focusing today primarily in the Rhino CAM suite of products. And the workflow would be very similar in all our other CAM products. Now, the 4-axis module is available starting with our expert configuration. So if you have expert, pro, or premium, you will have access to these 4-axis machining methods. You can do both indexed machining in 4-axis as well as continuous machining. Now the part that I have here, as you can see, the part requires machining from multiple sides. I'm just going to hide this block that's around the part so you can take a look at the part. So you have features that needs to be machined from multiple sides and multiple orientations. So parts like these can be efficiently programmed using indexed machining, where you orient the rotary axis or the rotary table to a given angle. You machine it from one side, so you lock the table at that specific orientation. In this example, we could consider orienting and locking it at 0 degrees and then milling it from the top. And then we perform what is called a rotate table setup. So that will turn the part on your rotary axis by the specified angle. So we could do a rotation of 180 degrees and program it from the other side, the bottom side. Now, the benefit of doing the indexed machining is you just have to zero it out once at your initial orientation. And once you've done it, the rotation, rotate table setup, and machining it from the other side does not require you to create multiple origins or multiples. You don't have to go back and re-zero it multiple times. That's the beauty of programming it as indexed using your rotary table or rotary axis in here. So we will go through the steps on how to go about programming this in here. So the first step is we would want to go into the Program tab in the machining browser, and then go to the Machine Tool Setup and set the number of axes under machine type to 4 axes, and the configuration to be a table, since it's going to be held on a rotary table, rotary check, so the part is going to be rotated. So we put the configuration as rotary table. In the next step, we want to make sure we specify our rotation center. If the rotary axis is aligned about the x-axis and it's going to be rotating the part around the x-axis, you want to make sure that the rotation center, as you can see, it's represented by this green arrow. When this machine tool setup dialog is active, you want to set the rotation center, the rotary axis, to the correct direction. So it could be either set to positive or negative x, depending on which way your rotary axis is set up, or if the rotation is along the y-axis, you could pick the Y for rotation. So in this particular example, we're going to leave it as positive X for the rotation. I will come back and talk about how to specify the rotation center. Right now it is set to the center of the stock material, and you can see the X, Y, Z coordinates are set to the center of the stock blank. Now once we've established the machine tool setup, in the next step, you would define your stock material. You could go ahead and select the type of stock. In this particular case, I'm going to be using a box stock, which is going to be just a rectangular piece of blank, where you can specify your length, width, and the height for the stock blank. And once you establish the stock, you can align the stock to the part. So very similar workflow like how we do it for other 2 and 3 axis operations. And then we set the origin, the program 0 or the work coordinate origin. So this would be done using set world coordinate system. And in this particular example, we are setting the origin to the stock material, highest Z, and the southeast corner. So the XYZ origin is being set to the top of the block and the southeast corner. Now, once this is established, when you place the stock blank on your rotary axis and machine tool, you're going to be bringing the tool down and touching off to zero it at this corner. So once you've established the origin, you'd want to go back into your machine setup and make sure the rotation center is being set to the center of your stock material, or the part material in this case. So we have an offset in the Y because the stock is 4 inches on the Y, so the midpoint would be 2 inches. And then since the height is 2 inches in the Z, the midpoint would be -1. So you could use the pick option and use the center snap and pick the center of the part here to establish your rotation center. So once this has been established, we are now ready to program our toolpaths. So the programming workflow for the top orientation, so when you look at it from the top view, this would be your initial orientation for programming. So this would be similar to how you program any 2 and 3 axis operation. So we will start out with a roughing toolpath. If you're using the Pro configuration, you can take advantage of all of your advanced 3-axis toolpaths as well when you program indexed 4-axis. If you're using the Expert configuration, you'll have still access to 5 different types of 3-axis methods, starting with horizontal roughing, parallel finishing, horizontal finishing, radial machining, and spiral machining as well. With the Pro, you can use all of the methods in conjunction with rotate table setups for programming index 4-axis. So we're going to start with a roughing operation, which is going to be horizontal roughing. We can select containment regions to contain our restrict toolpaths. We'll pick a tool for it, set our feeds and speeds. The workflow is very similar to how we program a 3-axis toolpath. The clearance plane is set to automatic. Specify the cutting parameters. In the cut levels, we can specify like a bottom cut containment to limit the toolpath not to cut past the mid plane, or maybe you can go slightly below the mid plane. So that way, when you machine it from two sides, there's no seam being left around the part when you rough it out from the two sides. You can either specify a cut level bottom, or you can insert a plane to also use that as your Z containment, and then specify your engage and retract parameters and any advanced cut parameters to generate your toolpath. So we now have generated a roughing toolpath, also known as horizontal roughing or Z-level roughing from the top. So let me go ahead and run a simulation of this. And there's our cut material simulation. I could also speed it up. And at any time during the simulation, you could even pause the simulation and select go to end to simulate through the end. So we've now roughed it out from one of the orientations. If you want to change, you can always, like I said here, go back in here and say cut level containment and set it to a certain height. So I'm going to go back in here and just go slightly below the midplane and regenerate the toolpath. You can see now, since I did not pick a containment, it's programming the entire stock, which was defined in here. I could go back and contain it to the stock extents in here. So our roughing toolpath has been regenerated, and we're only going slightly past the halfway mark. Now, once we roughed it out from the top, rather than doing a finishing from the top side, I would do a rotate table setup to rough it out with the same tool from the bottom half. So we would introduce what is called a rotate table setup, and this is how we index using 4-axis. So we can specify the table rotation angle, and based on the origin and the rotation center that you specified, you'll notice that your coordinate origin at 0 degrees is over here on the southeast corner, and as you rotate it, as you rotate the block, the origin still remains at the southeast corner when it's rotated, so you don't have to go back and re-zero it again at the machine. So that's the beauty of working with rotate table setups. Once you establish one origin, you're all set. So let's go ahead and program the roughing operation from the other side here. So I'm going to pick the same containment, and I'll specify the cut level containment in here as well to restrict it not to cut below slightly past the midplane. So we have now programmed the roughing from the two sides. I'm going to go ahead and run a simulation. And you can also see the cut material simulation from both the sides. You have the simulation from the top, and now you have the simulation from the bottom. I've just rotated the view so you can see that it's roughed out from both sides. Now, once the roughing is completed, we could go into a pre-finishing and a finishing operation. So we will program a parallel finishing operation in here from the 3-axis methods, parallel finishing. And I'm just going to use one of the operations in here, a 3-axis parallel finishing. And let's go ahead and run a simulation in here. So it's also known as index machining, could be 3+1 machining, where you can do a combination of 2 and 3-axis operations in conjunction with rotate table setups. So once we program the bottom side, we can introduce a rotate table setup again and rotate it back to 0 before we program the next set of finishing operations for the top, from the top side. So we have a parallel finishing program for the top side as well. So I'm going to go ahead and run a simulation here. And anytime you can do a pause and simulate to end. So we have it programmed from the two sides, and the part is now ready to be post-processed. So you want to make sure that you select your post-processor, the current post-processor. You can go to post and pick the post-processor from your list here. That's either listed by name of your machine or name of the controller, or it could be a combination of the two. And I'm just going to pick a FANUC post in here on the list. And then to post all 3 setups, the rotate table setups, into one posted output file, you just have to highlight machining job at the top of the tree here, right mouse button click, and then select post all, and this would post all operations into a single posted output file. And you'll see that the rotate table setups for the first orientation is A0, and the next one would be A180. You can look for A180. So the next roughing operation under setup is A180, and then it goes back to A0 to program the setup number 3. And then the part is now ready to be run on the machine tool. Now here's an example of what we did for how we did using 3-axis operations. I'm going to quickly go over an example on how we can also program using 2-axis operations using indexed machining. So in this particular example, I would like to machine these prismatic features that you can see right here. I would like to do a facing, a drilling operation and a profiling. So we could use our 2-axis methods, 2-axis operations. So we have a facing operation, profiling, and a drilling operation in here. Now to program this for the other faces, we could do the same. We can introduce a rotate table setup. And if I'm not sure what the rotation angle is, I can use select either planar curve or select a surface, and I can just go pick this curve, and you'll notice that the rotate table setup automatically determines the table rotation angle based on the curve that you selected, the planar curve. And I can pick OK now, and then I will go ahead and repeat the same operation. So I'm going to copy paste the facing operation. We'll go ahead and pick these 3 curve regions in here. I can select either the surface edge or I can pick a curve. So very similar to how we program 2-axis operations. I can repeat the same step for the profile operation in here and the drilling as well. So this is how we go about programming indexed operations, also known as 3+1, or you could even say use 2+1 if you're just programming a 2-axis operation. And then I can repeat the same process for each and every face in here. So now when I run a simulation, so we program 2 of the faces, so the part would be indexed so that the tool would remain normal to this particular face. So the part would be rotating on your rotational axis on a rotary table. And when you post process the tool paths, right click and do a post all. You will see the table rotation angle being output in here, as well as for the next setup here, you can see the table rotation angle is being output as 300 degrees to rotate the table, and then it continues with the facing, profiling, and the drilling operation. So the next topic we're going to be covering in today's webinar will be 4-axis parallel roughing and parallel finishing. So this would be using our continuous 4-axis methods. These continuous 4-axis methods are available and included starting with our expert configuration. You can access these 4-axis methods by selecting 4-axis under machining operations group from your program tab. And today we'll be covering the parallel finishing operation, and we'll talk about how the parallel finishing operation can be used also as a roughing operation. So it can be roughed in multiple radial levels. So in this particular example, the stock diameter is much larger than the part diameter. As you can see right here, I have this part and the stock displayed in here. So to rough it out from the stock to the finished surface of the part, we could use what is called 4-axis parallel finishing, and then we can specify radial step down to you program it using like a roughing operation. So we've covered how to program parallel finishing, 4-axis parallel finishing in our previous webinars. You can go back and revisit that. I'll quickly touch upon some of the parameters in here in this webinar. So we have the cut parameters, where you can specify your cut axial containment to specify the start, the low value, and then the high value is basically to contain the overall length of travel along the axis of rotation, and then the start and the end angle is for the entire rotational axis. Now, if you notice, there's a tab called Step Down Control in the 4-axis parallel finishing. This is where you can use this as a roughing pass, where you can specify radial cut levels by selecting the top for containing the the outer radius where you want to begin the cuts from, and then going down to the bottom cut level. And then you can specify the step down controls and how many radial step downs you would like to use to program this part. So the step down control is radially specified, and also you have the radial cut levels for the top and the bottom. Now, if you specify stock as 0, you'd be basically programming both roughing and finishing in one operation. If you specify a stock to leave, then this would be a roughing operation, and then you can go back and finish it with another profiling 4-axis parallel finishing operation. So I'm going to cover that as well in another example here. So in this particular case, we programmed it with multiple step downs, and I'm going to display the toolpath in levels, and you can see these radial step down levels, and we are stepping down about a 1/4 inch in each step. So I'm going to go ahead and run a quick simulation here, and it's going in a zigzag pattern, so which is basically cutting back and forth. So this would be our first step, 4-axis. So I renamed it as 4-axis parallel roughing and finishing. In the next operation over here, I'm doing a 4-axis parallel roughing just for one section of this part, and I've used a axial containment of specifying the low value and the high value, as you can see by these two planes that are marking, and specify to leaving a 50,000 stock above this part surface. So this would be used as a roughing operation, again using the step down control for the top, and then stepping it down by 50% of the cutter diameter. So very similar to what we did in the previous step. However, here we are leaving some stock, so we could go back and add another finishing operation. So I have now programmed the roughing. I have a 4-axis parallel finishing operation in here, which would basically take it down to the 0 stock, which is to the finished part surface, and I have not specified any step down control in here. So you could either break it up into roughing and finishing operations. You could be using different tools, different feed rates, or you could program it all as one roughing and finishing, depending on how you'd like to program. So this gives you an overview of how to use 4-axis parallel finishing for both roughing and finishing operations. The next topic I'm going to be covering here in this example is going to be 4-axis projection pocketing. This is one of the advanced methods that are available in 4-axis, and you'll be able to find this under 4-axis methods and projection pocketing. Now for the 4-axis projection pocketing toolpath, you will have to select a control geometry. The control geometry could be a closed curve, or it could be a chain of edges, surface edges or face edges, which you could select, or you could even pick a surface boundary as long as it forms a closed loop. And you pick a tool for it. In this particular example, I'm going to be using a ball mill. Set your clearance. The clearance plane is set to automatic. And then we have the cutting parameters. Now this 4-axis projection pocketing is similar to our projection pocketing we have in 3-axis. So for those of you who have the Pro configuration, you're familiar with the 3-axis projection pocketing. So this is a 4-axis projection pocketing where the tool, the cutter will stay completely inside the pocket boundaries that you select the control geometries. And you can either choose your cut pattern to be a 2D, like an offset, so which way 2D offset would basically use the curve region and create successive offsets, or you could use a linear cut pattern as a lace cut pattern to have it programmed back and forth. And you have the options to specify your cut direction, your offset starting as the inside or outside. You control your step over parameters. We also have an option to specify step downs that we've introduced in our latest version. We'll cover that in just a moment. So selecting generate generates the 4-axis projection pocketing toolpath. And this can be used for programming pocket features that are required to be machined on a rotary axis setup or a 4-axis setup. Now this could be a finishing operation. To program this as a roughing operation, you could specify step down control, where you can specify a radial cut level top, And you can also use insert multiple step downs and specify your step down control either as % tool diameter, distance, or number of levels, and then pick generate. So this creates multiple radial step downs for your 4-axis projection pocketing. So let's go into the simulate tab and select play to run the cut material simulation. So it's taking the finishing path and offsetting it up in multiple radial levels to create a roughing path. So I could program it as one operation for both roughing and finishing, or you could program this in one or more operations to have a separate roughing and a finishing operation. Or in this case, I've combined it to one operation where both roughing and finishing are programmed as one. Now to program the other pockets, which are identical, as you can see right here, and they are in a pattern, we could, rather than having to go through the process of programming each and every, by picking region as a 4-axis projection pocketing, we can automate our programming workflow, make it easier by using this feature called Rotary Instancing. So with the Rotary Instancing, you can specify the angle to increment it about. So the table increment angle, rotation angle is set to 60 degrees, as these are 60 degrees apart, and you can specify the number of additional rotations. So when you specify this, you generate it, and you take the 4-axis operation or any operation that you'd like to instance, and you place it inside the Rotary Instance folder. This will automatically instance and apply the toolpath when you have a pattern that's repeating itself at a constant rotation there. So here I could just program one of the features and then apply a Rotary Instance to automatically repeat itself multiple times. So when we go ahead and run a simulation here, you'll notice that the 4-axis projection pocketing is repeated for all the patterns at every 60-degree increments. So this is a great way to make your programming workflow a lot easier, simpler. This can also be done for when we do index machining using rotate, instead of doing rotate table setups for each and every orientation, we could use the Rotary Instancing to repeat that multiple times. So I'm going to go ahead and speed up the simulation in here. As it repeats the Rotary Instance for each and every 60-degree rotations. So it's performing the last instance right here. And when we post-process the toolpaths by selecting the entire setup in here, the instances are also output and computed. So I'm going to go ahead and look for Rotary instance. And you'll notice that here the first Rotary instance is output right here at an angle. And then we can look for the next instance, which gets repeated itself automatically. It computes the angles for each of the instances. So you have instance 2, instance number 3, 4, and then 5, final one. Now the same can also be applied for the other example we worked on in this case. So rather than having to program this particular rotate table setup in here, I'm going to go ahead and replace this setup. I'm going to delete this by doing a cut, and I'm going to introduce the 4-axis Rotary instance and specify the table increment rotation angle and the number of rotations. I'll take these 3 operations in here and place them in the Rotary instance, and you'll now see that it's automatically being instanced 6 times at every 60-degree interval. So this improves your productivity and be able to program your parts at a much faster pace. makes your programming easier, having to fewer, you just have to program one of the instances and then you can just repeat it. So this is a great way to.
I think you went a little quick there. I just want to make sure people understand how quickly you did that. Just created one operation and put them under Rotary Insyancing setup, and voila, you got this whole part machine. So I want to make sure people understand that and they can take advantage of this really cool functionality. If you can go with that pretty slowly, that'd be great.
Sure. I'll go back and reload this part here. So what I currently have, is a facing, a profiling, and a drilling operation just programmed for one of the instances, just one of the areas. And I want to repeat the same for the remaining additional 5 orientations. So rather than programming each and every face by creating a rotate table setup and then programming a facing, profiling, and a drilling operation for each of these, I'm going to introduce using what is called a rotary instance from the 4-axis menu. You specify the increment table rotation angle. In this case, we have 6 of them, so 360 over 6 would be 60 degrees increment. And then the number of additional rotations, we already have programmed 1, so that would be 6 minus 1 is 5. So number of table rotation is 5. I'll click generate. So once the rotary instance has been created, we just have to take these 3 operations and place them into the rotary setup folder, so like a parent and a child. So once you place it under the rotary instance, you can see the toolpaths are automatically instanced for the rotation increments at 60 degrees each. And now when I go to the simulate tab and I can run a simulation here by selecting the rotary instance, you'll see all of the instances are programmed. And when you post-process the toolpath, it'll automatically increment them by 60 degrees each. So this makes the programming a lot simpler without having to program each and every face. So this could be done for both indexed as well as continuous 4-axis, like we looked at the previous example with the projection pocketing toolpath where we could apply a rotary instance as well.
Yeah, and the instancing can be applied to 3-axis operations as well, not necessarily 2.5-axis. You could have a sculpted face on one of the faces or on all the faces, obviously, and you could have run a 3-axis operation. Actually, you could have run multiple 3-axis operations and fine-tune it, and then finally do the rotary instancing. It can be a big time saver. Thanks, Uday.
Thank you, Joe. Okay, so we will now move on to our next topic here in the list, which would be our drive surface machining. So we'll cover that by taking a look at an example here for 4-axis drive surface machining. The drive surface machining is also known as, also can be called as true 4-axis machining. So we have different types of 4-axis techniques, programming techniques. We have the indexed machining, we have the continuous machining, which could be made up of a wrap, where it's used on a part with a constant radius. We have a projection type of 4-axis machining, which we looked at in the previous example, which could be like the 4-axis parallel finishing, the 4-axis projection pocketing, and then we have this 4-axis true 4-axis machining, also known as a drive surface machining, where the tool remains normal to the surface at all times. So drive surface. So in this particular example here, we have modeled a surface. It could be a surface that's formed using surface of extrusion, or it could be like a rule surface that you can see right here. And this is very effectively used for machining, where in most cases when we do the continuous 4-axis machining, the tool would remain normal to the rotational axis. In this particular case, the tool remains normal to your surface that's being machined. So in this 4-axis method, the drive surface machining is also available in expert and higher configurations. So To program a drive surface machining, you will need to actually have a NURBS surface that you can create in your host CAD system. If you're using Rhino, you can model the surface like a surface of extrusion like you see right here. And when we go into the 4-axis drive surface machining toolpath, we will actually have to pick the surfaces that you'd like to machine. So in this case, we've selected these 4 surfaces, the top, the 2 sides, and the bottom. And you also want to make sure that the surface normals are pointing in the right direction. If you need to reverse or flip the normal direction, you can use these controls in here. You can select and either do a flip a normal for an individual surface, or you can say flip all normals to flip all the normals if the normals are not pointing in the correct direction. Now, once you have these surfaces selected in here, the next step is to make a selection for the tool, the cutting tool, set the feed speeds, and then we go to the clearance, very similar to the other 4-axis operation. In the cutting parameters, we have different types of cut patterns, similar to what we noticed in our 4-axis parallel finishing. We have a long axis, a cross axis, and also we've now introduced helical cut pattern in the drive surface machining with our latest release. You also have the option to specify your cut direction, could be zig or zigzag, and then you can choose whether you want to begin from low to high or high to low. So, and then you can also reverse the cuts. So let me go ahead and generate this path right in here, the 4-axis drive surface machining, and I'm going to run a simulation so you will see how the tool remains normal to the surface that's being machined. So I'm going to do like an animation first, and then we'll go ahead and do a cut material simulation. So you'll see that if I slow down the simulation in here, and we'll go to one of the end views, you can see that the tool is being normal to the surface that's being machined. So in this case, the y-axis also moves as the x and the z as well. So you have 3 linear axes and the rotational axis in your output. So you have x, y, and z and your rotational axis. So the tool is being normal to the surface that's being machined. Now let's take a look at this in a cut material simulation. I'm going to display the stock for simulation. And also I'm going to enable what is called a machine tool visibility. So we can perform machine tool simulation with the machine model. We can pick a machine tool by selecting load from file. And in this case, I'll just pick a generic machine here. I just picked the Tormac. And let's go ahead and run the simulation. And you'll notice that in the machine tool simulation, you can see that the y-axis is also the table is moving back and forth in addition to stepping forward in x and also moving up and down in z. So this is a true 4-axis machining where all 3 linear axes and you have a rotational axis involved. You can also machine features that are dipping below the center of rotation when you program a true 4-axis machining, or it's also known as drive surface machining. And I will go through that with an example as well. So let me go ahead and pause the simulation in here. And I'll switch back to another example where we can cover how the drive surface machining can be used for other class of parts. Okay, so what I have here is a 1/2 of a mold for a ring. And I've switched the view to like a ghosted view. So what I've introduced here is I've created a drive surface that's underneath the cavity of the mold. So as you can see, the drive surface is over here on the inside. So let me hide this model. So you'll see that this is the drive surface we've created, and you can see the drive surface is dipping below the center of rotation. And we would program a drive surface machining toolpath by selecting these surfaces. And in the cut parameters, we have the option to project it to the geometry. So the tool path would be normal to the drive surface, but projected to the geometry that's visible here, which is the mold cavity. So by doing this, you could program intricate features and the tool would remain normal to the drive surface. So let's go ahead and take a look at this simulation in here for the drive surface. So as you can see, the tool is being normal to the drive surface, but it's following the geometry which is being projected to.
Another nice feature about this particular machining method is you can use this for machining complex meshes as well. So you can create a drive surface to define your tool drive path and then project it. Basically, you're projecting it onto a mesh surface, which can be quite complex. So obviously, the drive surface should be somewhat close to the mesh shape to get good results. But instead of having to deal directly with the meshes, you can use this method quite effectively.
Thank you, Joe. So the drive surface could be like a surface of extrusion, and the curve that you select for the surface of extrusion could be normal to the axis of rotation, and you can pick that as your drive surface. So in this case, we are using a cross-axis cut pattern for the drive surface machining. And in the next operation, we could do it as a finishing operation as well, where we had chosen a long axis as the cut pattern. So we could use the different cut pattern types that are available for drive surface machining. So we will take a look at the posted code in just a moment as well. So for features that are dipping below the rotation centers and other kind of intricate features, this is a good way to program it. So you have a wide range of options available to program using indexed and continuous 4-axis machining, starting with our expert configuration. Okay, so let me go ahead and switch back to the previous example we were on. And I'm going to go ahead and post-process this toolpath. Right-click and do a post. I'll select the post processor in here in the list here. I'll just pick a generic FANUC post and post it out. So you will notice that here in the posted output, you have your X, Y, Z, and then in this case, A is being the rotational axis. So the Y and Z and A, they all change. Okay, so the next topic we'll be covering in today's webinar is the R-level finishing methods. 4-axis R-level finishing, which is similar to our Z-level finishing in 3-axis toolpath methods. And this can be used for features where you would need to machine features where you could have like drafts or extrusions along the features along the rotational axis. So here I have an example of a band where there is these extrusions like cavities like here, which they are steep sections or steep walls that needs to be machined along the rotational axis. So to program this efficiently, you could use the 4-axis finishing in levels. This is also called R-level finishing, which is basically radial level finishing. The method is similar to our Z-level finishing that we have in 3-axis methods. So if I take a look at the 4-axis R-level finishing toolpath here, you can pick regions to contain your toolpath. So I've selected these regions and I'll pick a tool. In this case, I'm using a taper tool to get a draft in here. And in the cutting parameters, you could specify a cut direction. And in the cut levels, allows you to specify the radial step down control, and you can also contain the top and the bottom cut containment for the radial levels. So this would generate or produce a R level or radial level finishing toolpath. So this can be used for like prongs or features that are sticking out, or it could be like, like steep pockets that you have where you have draft on the sides of the part. So you could use 4-axis R level finishing toolpath for these. Let me go in and run a simulation here. So I'm going to quickly run through the simulation of the 4-axis pocketing, which could be used as a roughing toolpath. We've covered this in our previous webinar, how to program 4-axis pocketing. You can refer to that. And once this simulation is completed for the pocket, we'll do the simulation for the 4-axis R level finishing in here. So as you can see, it's stepping down in radial levels, and then it transfers over from one region to the next.
One quick note on the R-level finishing and R-level roughing as well. There is no X or Y movements here. So it's not a true 4-axis operation. It's very similar to our projection methods, where the tool remains normal to the rotary axis. The only continuous method that we have in our system is the drive surface method, which will actually make the tool move in 4 different axes at the same time. So I hope that's clear.
Okay, so we just completed the simulation of the 4-axis R level finishing. The next thing we're going to cover here is in today's webinar is the feed rate options in 4-axis. So by default, the feed rates are output for 4-axis or multi-axis toolpaths are units per minute. If you're programming in inches, it would be inches per minute. If you're programming in millimeters, it would be millimeters per minute. So this particular part is in millimeter units. So your output, when you define your feed rates, the feed rates are set in the units per minute format in here in the feeds and speeds tab. The same goes with parts that you have programmed using inch units. So I'm going to go into another example where I can bring in an example with the inch units as well here, so which we can take a look at that. So we have an option. So when you post-process these toolpaths, they're basically output as units per minute. That's the default output. So when I go ahead and do a post-process, let's say we want to take one of these operations in here and do a post. So it's output in, feed rate is output in whatever the program feed rate is, which is units per minute. Now we do have the option to output multi-axis toolpaths using what's called inverse time feed rate. So in order to output inverse time feed rate, you would have to go into your post processor, edit the post, and then under the feed rate section, you would go in and enable inverse time feed rate. So the code to turn on the inverse time feed rate is going to be typically a G93, and then a G94 will basically restore it back to units per minute mode. So inverse time feed rate is enabled or toggled on by using G93 and the G94 to cancel it. And so we also want to make sure that the feed rates are set correctly, the high and the low value. So I'm just going to go ahead and bump up these numbers here for the feed rate high and the low value here. I'll set it up, I'll just increase it, and then we'll save the post. Now, when we post process the toolpaths, the feed rates now are computed in inverse time. So when you post it, you'll see that the feed rates will be in inverse time, which means that each and every line of code will have a feed move for every line of code. So you just have to, when you post it out again, you will see that the inverse time feed rate is output in here, and the feed rate changes for every line of code. So that's what the inverse time feed rate does. You can enable this by using a G93 in the feed rate section by selecting output inverse time feed rate, enable it by G93, and then cancel it. So this is only output on a multi-axis toolpath. So you would use G93 to enable it and then G94 to cancel it out. So if your controller supports inverse time feed rate, you can enable these options in the post processor and then post process your toolpath. Now the final topic for today is the 4-axis options that I'll be covering. The 4-axis options can be found under the 4-axis in the group under machining operations group. So we have 3 different options in here. Option 1 is always retract to tool change point before each table rotate operation. Now this is helpful when you're programming indexed operations. So I'm going to go back to this part we programmed in our webinar earlier today. So when you program indexed operations, and in this case, the part we have has, the width of the part is almost 2 times the height of the part. So when the part rotates, you want to make sure that your tool is out of the way, fully clears out of the way, so that it doesn't snap the bit when the part is rotating on your rotational axis. So you can enable the always retract the tool to a tool change point before each table rotate operation and specify a tool change point in here. So in this particular example, we have set a tool change point of X is 2, Y is 5, and then Z is 3. So it's basically going to back off the tool on the Y axis by 5 inches, move it up into Z, and then this is output before each table rotate table operation is performed. So when we post process the code, as long as you've specified a non-zero value for the rotate table setup for the tool change point, it'll move the tool to that location. So if I go back and search for the next table rotation in here, you will notice that before the table is being rotated, it moves the tool to the safe location and performs a rotation. So this, helps you determine what tool change point to set. And you can basically use that this option is checked by default in 4-axis options. Always retract tool to a tool change point before each table rotation. Now, if you do not specify a tool change point and leave it at 0, 0, 0, it will not output the tool change point because we don't want you to crash into the table. So only when these are set to a non-zero value, the XYZ coordinates will be output before each table rotation. So this is a very useful tool to retract the tool out of the way before you perform a table rotation.
Yeah, this tool was this option was put in for machines that don't have an automatic tool changer. So there's no automatic machine command to go and change the tool. So you'll have to manually retract the tool up somewhere, to a safe point, and then change the tool, and then come back in and machine it. So that was the motivation for this option. Thanks, Uday.
Thank you, Joe. So the next option we have here is always warn if rotation center is not aligned to X or Y. Now, considering that we are doing a 4-axis continuous operation, continuous operation, and when your XYZ origin and the rotation center are not aligned and there's an offset between the two. So in this particular case, if I want to program a 4-axis finishing operation, you will see that the rotation center is at the center of the piece, but the XYZ origin is offset, which is at one of the corners of the block. So when you try and program a 4-axis continuous toolpath, so in this case, if I choose a 4-axis parallel finishing, I would be warned saying that the rotation is not in the center of rotation. So the origin and the rotation center are being offset. So some machines are not capable of handling an offset where the rotation center is offset from the origin that you established. So this is just to let the users know that you're aware that you have an offset between the origin, your program origin, and the rotation center, and your machine is capable of handling it. So you can ignore this by saying do not show this again and then pick OK to continue programming it. So this is just to help the users out. So if the machine is capable of it, then you can just ignore it and continue. If the machine is not, then you need to make sure that your XYZ origin and the rotation center are right, right on top of one another. So in this particular example, if I go back into this particular file, you can see that the rotation center and the XYZ origin are coincident, or basically, at the exact same location. So if the machine can handle the offset, then you can, set the origin and the rotation center with the offset locations. Now, the last option we have is do not output intermediate points for transfer motions. So this is this basically will eliminate the intermediate points from going from point A to point B for transfer motion. So in this particular case, you can see there's a transfer going from the end of one region to the start of next region. So when you select the option to not output the intermediate points for transfer motions, it's going to skip all of these intermediate points and just output point A and point B. So just, in some controllers, it just makes the rotation much faster and easier. So it's going to skip those intermediate points when you post-process the toolpath. So the option to not output intermediate points for transfer motions. So these are rapid motions. This will be skipped, every point-to-point move between regions, or when it transfers from one region to the next region. So with this, I would like to conclude my part of the demonstration today for the advanced 4-axis topics. And I would like to hand this back to Joe.
Thanks, Uday. Thanks again for a good demonstration of our advanced 4-axis options in our system. We have a few more minutes here to answer your questions. We can pause here. Is there anything that users would like Uday to show? This would be the best time to ask. If not, looks like we don't have any questions. We'd like to wrap this up. And as usual, you can contact us by phone, email, Skype, or chat, whichever is convenient for you. We're available. Like we say, we are your CAM partner. So please drop us an email if you have any questions. And as I mentioned before, we will send out the recording of the webinar later today or sometime tomorrow. Again, thanks for attending, and we will see you next month. Take care. Bye-bye.